So we have seen the equalization on the voltage mode output driver, and let me just summarize. If you have any questions, sure, feel free. Equalization on or voltage mode output driver. Say equalization voltage mode output driver. And okay, so let's see what all we have seen. We have seen by creating a resistive divider, we can create a different output voltages which is required for the equalization. That is varying conductance linearly. If you remember, this is like 1 by RT, 1 by RS, R up and R down, varying linearly with output swing, right? Varying conductance linearly with respect to output swing. But this has a non-linear and increased power consumption. This is the one which we saw. The second one was varying conductance non-linearly. Non-linearly, if you have seen, that was with respect to like V out square terms were coming. Non-linearly with respect to output swing. And this has a constant current consumption. Constant current consumption, which is equals to VDD by 4 times RT. The third one which we have seen was again like where we didn't have a R down resistance, which was varying conductance. There also it was a non-linear. There was a linear thing, varying conductance linearly with respect to output swing, and this has a non-linear but proportional current proportional to output swing. Output swing. So let me just say here the current was non-linear proportional output swing power consumption. Okay. And in the very last, we saw the pulse width modulation or time-based equalization. And this had a constant current consumption. Sorry, this was proportional to the output swing you want. You can say it's a linearly proportional to output swing, or relate. Let me just say directly. That will be better. Say directly proportional to output swing and linear in fashion. Okay. So we have seen like 4 different kind of equalization at the transmitter output driver. Do you have any questions in any of these techniques? Okay. So, and the implementation of this can be done on full swing output driver also and limited swing output driver, each of these. The implementation is just like changing the switches there. The only the drawback of a non-linear, let me just highlight this, that non-linear variation in conductance actually leads to more power consumption in pre-driver. This is one of the drawbacks. So if you are saving any power in a like having a nonlinear conductance by having a constant power, it may lead to increased power consumption because of the finite resolution of equalization you want. Is there any doubt in this or any confusion? So the thing is, whatever swing you want, it will remain constant. So during equalization, the swing will not change. That's the thing, means you vary the duty cycle, and that's how you vary the output swing. That's how you vary the equalization number. Current consumption remains constant. So let me just give you a very brief thing. So let's say, okay, so let's say these are the bits which I want to transmit. Let's say this is the data D. Okay. If you are doing a voltage mode of equalization, let me just have a, you see the difference. So let's say if you are doing a voltage mode of equalization, so just let's say for the first bit, what should be the output? Voltage mode equalization is like you can say H of equalizer of n is equals to something as 0.8 times d of n or delta of n is writing as equalizer. So this is delta of n minus 0.2 times delta of n minus 1. Okay, if this is the equalizer, no matter whichever way you implement, right? So the output of the equalization for with like in this format will be, so if I look at this, this will be, here the output will be 1 correspondingly. Then you have 0.6 for example, and then when you go to minus 1, then you will have minus 1, right? Then for the minus 1, you will again have minus 0.6, minus 0.6, and then you go to plus 1. You got this, right? This is the equalizer output, means this should be the output coming out of the output driver. So let me just say this is voltage mode equalization. Now what will happen in a pulse width modulation with equalization is, let me just try it again. So when it is positive 1, for the positive bit it will basically have, let's say, some percentage of duty cycle and smaller. So if this is, sorry, if this is positive and negative, so I should have, so it will be something positive for a while. This one is positive for a while, then becomes negative. So this is the one bit. For a negative bit, it will be this. Sorry, it's still again positive. The bit is positive, so then again you go here, then again negative. For a negative bit, you are negative and positive. So this is the output of PWM equalizer. No, here each pulse width is modulated. Each bit is modulated. It's not that it is modulated only when you are having plus 1 1. So it is independent of the previous bit. So the current pulse itself is modulated by the pulse waveform. So this is independent of the previous bit. It doesn't depend on the previous bit. There are only two waveforms here. So you can say whatever bit is coming, if, let's say this is d of n, right? It goes to a pulse waveform which is, let me draw it a bit bigger. So it goes through this kind of pulse waveform. This is 0, this is time period t, and this is d times t, plus 1 and minus 1. So this is the pulse waveform for a PWM equalization. Whereas for your voltage mode equalization, that is NRG. NRG is, for a voltage mode equalization, you have this, right? It's either positive or negative, it remains same for 1 bit period, and then you combine the two different bits for the equalization. But here you are doing for each bit, you are having a same pulse waveform. So if you see the transmitter output, that has only two output voltage levels, plus 1, minus 1. Okay. Why output string can be variable? Yeah, so this particular equalization is restricted by the bandwidth of the circuit and all. Yeah, those hybrids have been used. So like hybrid of PWM. Okay, so there can be very distinct variation. So I can apply this PWM modulation on these pulse widths also, right? Certain amount by this and certain, you can do that. Or even you can have a different pulse width. Here I have used only D factor, like one single factor, right? Depending on the bit pattern, I can use a different pulse width also. So those things also have been used. But the problem comes is when you try to, so how do you create this tunable duty cycle? So how much power is spent in creating that duty cycle? Then what are the blocks which are processing? Because surely this PWM pulse width modulation is requires a higher bandwidth on the circuit components which are using. So there is a limit to it. You cannot do much beyond that. But a hybrid thing is there. Pardon? Yeah. So if a question is that, let's say for the PWM, this is a pulse width response. So let me just write it. So for a, okay. So output of a voltage mode equalizer is equals to your D of n convolution with H equalizer of n, and if I assume this is equals to delta of n, let's say just for example minus 0.2 delta n minus 1, so this is equals to your convolution is with this, right? So you will have 0.8 times like this, d of n minus 0.2 times d of n minus 1. This is a voltage mode equalization, right? Now, whatever I have written, that is being written in a form that I am only considering one single sample, d of n, that's a 1 point, right? So you actually have, can say d of n goes through a pulse waveform, NRG pulse waveform, where it remains for 1 bit period. Okay. Now, if I go for a PWM equalization, so this is just in terms of, you can say, in one single sample. But if you want to write the same thing, let me just complete this part. If I want to write the transmit signal for the pulse width, for the NRG modulated waveform, that will be equal to, so you see, so this will be at any given time, let me just write it in this way. this whole thing is convolved with your pulse waveform P of t, which in case of voltage mode equalization is equals to u of t minus u of t minus t, where t is your bit period, right? Did you get this part? That the actual transmit waveform is not like a single impulse. Actual transmit waveform is whole pulse which you transmit for one bit period. Okay, so you can write this expression that how will it actually say like u of t minus capital T, which I am using as a bit period, when convolved with your actual equalized signal, then it will be summation of your now this is like I am using a discrete and continuous time both here. So this will be 0.8 times d of k minus 0.2 times d of k minus 1, right? And this will be p of n times, so let me just say p of y of t, this will be t minus kt, where now here the t I am writing, that is t is in between k t less than k times t plus 1, sorry, this is all the sum. So here you write this particular t, let's say in between n times t times n times t plus 1. Pardon? So this means at given time your t is valid only, the time which I am writing is valid only for that. I didn't get it. Oh, sorry. Yeah. So you need to write the whole expression if you want to see the effect of the PWM equalization in comparison to PWM equalization. Now what will be done for the PWM equalization? Your P of t is equals to u of t minus, so how will you write this equation? So u of t minus u of t minus dt is this portion, right? Minus u of t minus dt minus u of t minus t, which is equals to okay. So this is the pulse waveform which we are using for equalization with PWM in comparison to only a NRG pulse. So for analysis you use this waveform. So if I want to write y of t, that is equals to, you can say, convolution of your d of n t with your p of t. It becomes a little bit more involved if you want to write the frequency response of this waveform. An important thing here is, if you look for NRG pulse, right? So we are considering an NRG pulse which you have seen here. Where did I write it? Okay, let's say NRG pulse waveform is u of t minus u of t minus t, which is p of t. So p of f is a sinc function, right? And that sinc function actually has a null at 1 over t. Can you get this thing? So when you are transmitting a pulse waveform, this is equal to convolution is equal to multiplication in the frequency domain. You are transmitting an NRG pulse. The NRG pulse has a sync waveform which has a null at over 1 over T. Okay, but what actual thing is, if you write for PWM, for PWM waveform, which is u of t minus 2 times u of t minus dt plus u of t minus t. The actual thing is actually it doesn't have a null at 1 over t. It's something else, you can work that out. So, to a given extent, NRG pulse waveform actually, PWM pulse waveform actually provides a wider equalization because NRG is having a null at 1 over Fs, but this thing doesn't have it. The PWM pulse doesn't have it. So, if you look at so this is just the pulse waveform, right? So let me just show you the equalized waveform. So we know that the equalizer will be something kind of this, right? Let me just plot it as a, okay, this. So equalizer will be, this is all the equalizer which we are considering are like this. Let's say this is a log scale and I put it this as 1 by 2t, like Fs by 2. So for the rectangular pulse waveform or NRG pulse waveform, the equalizer response which you will try to look, that will be something, this is 1 over 2t, this is 1 over t, and let me just say if the sync waveform is something kind of this. Then for NRG pulse waveform, the equalized waveform is in this manner, where you see that you are not actually equalizing beyond Fs by 2. Whereas for PWM, you can have a similar thing passing through the same point but having a wider frequency extension. Like you have more emphasis even beyond Fs by 2, which is not there in case of your NRG pulse modulation. So in this case, PWM actually wins. But you can say like in PWM you are having only one control, which is the duty cycle. In case of NRG pulse modulation, if you use multiple taps, then you have more control over it. So you can have a very different channel you can try to equalize, but that constraint is very much constrained in PWM equalization because you have only 1 degree of freedom. If you want more, then you try to use more different pulse width, that is more extension of it. So if you compare, if you compare FIR equalization, FIR2 and PWM, FIR2 means 1 tap, means 1 additional tap. It is normally called as 2 taps. So in case of all the FIR equalization, if you see there is 1 main cursor and 1 pre or post, that is like total 2. So the main cursor is also called as an additional tap only. So 2 taps means 1 main cursor plus 1 pre or post only. Pre or post, that is 2 taps. So if you compare FIR with the PWM, which has only 1 single duty cycle control, in implementation, you will find that PWM can compensate more loss. You don't compare FIR3 with PWM with only 1 single control. for smooth channels. But this comes with a more power penalty because the circuits are processing now a higher frequency signal content. Okay. Any questions? Duty cycle is not based on, duty cycle is decided based on the channel loss. So here duty cycle is the control which will cancel the ISI. Right? So last time, I don't know if you remember, so in place, so let's say this is one bit which you want to transmit. Okay? This is time t, this is capital T, and this is one amplitude. What did we do? So if you do not do anything, let's say you transmit the same pulse, the output pulse will be something kind of this. Amplitude attenuated, skewed, this pulse, right? So you have all these ISI points. In place of this, we transmitted for a duty cycle pulse, we transmitted something like this, plus and minus 1. What happened? The output pulse, you will see a lesser amplitude to begin with, because just consider the output response of the channel for the positive part of the pulse. Okay? If you are having a smaller pulse, then you will have a smaller amplitude, right? Then you consider the output response of the negative part of the pulse, which will be something like this. Now, the output, if you look at the, so if you look at the peak points and one bit apart, this will cancel out, right? So the equalization you can think of, if you are looking at time domain, you can think of a superposition between the positive pulse and the negative pulse to lower the ISI. Okay? That is the time domain picture. If you want to look in a frequency domain picture, you can say that within a one period, I am having more transitions. Earlier in a one bit period, you had only one transition, right? Positive to high or high to low or low to high. Whereas in this case, you are having more transition in a one single bit period. More transition in a same amount of time is equivalent to more high frequency content. So if you want to think of in terms of a frequency response, how you equalize, you can say by PWM, we are introducing more high frequency content, right? So does the picture become clear in a frequency domain and time domain both? Time domain, you see superposition of a positive and negative pulse. In frequency domain, you see that more transition within the same amount of time, so high frequency. Okay. So any questions on this? The thing is, we will move on to the receiver side after this. So if you have any question, feel free. Okay. So one last thing about this thing, about the equalization on the transmitter side is that it's easy to implement equalization because the bits which you have are like a well-defined positive or negative signals which you need to equalize. You have the whole bit pattern on which you apply the equalization. So the problem arises is that there is a finite supply on the transmitter side. So if you have a finite supply on the transmitter side, it actually leads to your reduced amplitude on the receiver side because you cannot amplify the signal on the transmitter side beyond a certain limit. So let me just show you with example that let's say the channel response is 1 plus alpha Z inverse. Okay. Now if I want to have an equalizer which completely cancels the channel in an ideal fashion, that should be equals to 1 by 1 plus alpha Z inverse. Right? So my output of the equalization, which will be, or you can say the transmit signal, my transmit signal ytx of n is equals to your d of n convolution with h equalizer of n. Now, where does the limit come? Limit comes that Vtx, that the maximum of Vtx is limited by supply voltage. If you try to do, you will saturate. That's a concept. Okay. So what will be the maximum ytx of n? So if you look at maximum ytx of n, if I write, so okay, ytx of n is equals to summation of d of k in convolution with h of equalizer n minus k. Okay. Now I want to find a maximum. So before finding the maximum, and here you note that I am using an ideal equalizer which I cannot realize. So we are doing the best possible. So h equalizer of n is equals to 1 plus, okay, so let's let me just put it in a different manner. So h equalizer of z is equals to 1 plus alpha z inverse minus 1 under the constant that mod of alpha and z is less than 1 for the binomial expansion. This is equals to minus 1 k alpha k z minus k. Right? This I think everyone there is a binomial expansion, nothing more. So h equalizer of n is equals to summation of minus 1 power k alpha k delta of n minus k. Right? Now if I want to find maximum of ytx of n, that will be equals to, now d of k we know these are the bits, so this can be positive or negative. Okay, so that is equals to, I will apply a mod on this, right? Minus 1 power k, or you can say if alpha is negative, which is not, and delta of n is 1 or minus 1. That's the maximum value. So what you have? You have summation of alpha power k, which is equals to 1 by 1 minus alpha. So if you are not, right now I have not yet limited, I am just finding what's the maximum value. And you see that this maximum value is dependent on alpha. As alpha increases because of the increased channel loss, right? Your maximum value means maximum of the transmit signal swing actually increases if you do not do anything. Okay. So if I want to limit it by the supply, what will I do? So this is without limiting by the supply. If you are increasing alpha, your output swing is increasing. If I want to limit this value, what should I do? No, alpha is a channel thing. So if my alpha increases, I have to change the alpha here. But at the other point I am limited, so I have to normalize something, right? Normalize the output transmit amplitude. Okay, so let me just, this is you have seen as an ideal equalization. So if I want to normalize, let me just say, so there is certain limit like my supply voltage. So let's just write it. This is an ideal equalization. Regard that this is an ideal equalization I am doing, right? If I want to normalize with the maximum value which it can attain at any given time, you have a question? Oh, so you see that ytx of n is equals to convolution of d of k h equalizer n minus k, right? And h equalizer of n is equals to minus 1 power k alpha k delta n minus k, h equalizer of n, right? So ytx of n, if I write, that's a, so let me just, so here only, if I say ytx of n, I am doing a convolution, so this will be minus 1 power k sorry, what's happening? Alpha k, okay, then d of n minus k, right? Did you get this part? Okay. Now, what is the maximum value of y t x n? Given that d of n can have a value plus minus 1. Modulus of that, right? So, modulus of that means when minus 1 is, think this way, when k is basically 1, you choose a negative bit, means you can attain this situation depending on the bit pattern. So, I am just trying to create the first bit pattern in which it can go to a maximum value. So, then it will be summation of alpha power k, and summation of alpha power k is 1 by 1 minus alpha, given that mod of alpha is less than 1. Right? So what I'm here is that if the equalization coefficient is varying, alpha is varying, so the maximum value which you are getting due to equalization also varies. But I do not want to get, means I cannot basically increase my maximum value because I am always limited by the supply. Okay. So what will I do? I will normalize the equalizer with its maximum value, and then, so this is, if you look at this transfer function, right? Here I normalize the value, maximum value. So this whole transfer function has a maximum value of 1. Then I have this V supplier. Whatever V supply is just like a one single voltage which I use. Okay. So now if you look in terms of your final, means if I say what is the received signal, right, that will be ytx of n in convolution with h channel of n, right, and h channel of n and h ideal equalizer of n is 1. Okay, so this is equals to 1 minus alpha times V supply. Ideally means you are compensating the channel very exactly, there is no difference here. But what you see, as your loss changes with respect to alpha, your output signal swing also changes. There is no frequency term here. It's like you are scaling the final amplitude. So does it convey the point that supply limit actually lowers your received signal swing? Right? This is one of the reasons that you cannot do a lot of equalization on the transmitter side, that your signal swing at the received end will just reduce. So, since there is a limit on the transmitter side, you go and try to do the equalization on the receiver side. There are other reasons also, but this is one of the reasons. So what is there on the, so why the things are not limited on the receiver side? So let's say this is the received signal, sorry, this is a receiver end terminated by RT, and this is, after this you will put an equalizer, right? The same block, whether you put, it's a linear system, you put on the transmitter or receiver, it should have a same effect. The thing is that the received signal is already lossy, so the received signal is already lower in the swing. So you have more range to amplify. There will be problems with this also, but because when you are amplifying the signal, you will amplify noise also. That's a different case. But you have more range to amplify, more here you see that I have used only one single alpha. Here you can have a larger alpha also, you can try. But again, means you will always be limited by what's the final supply swing. But here you are having more headroom. So it's like if I am having a 1 volt swing here, if the received signal is only 10 millivolts, I have a gain to go larger. So most of the time, when you amplify the whole signal itself, that is called as pre-emphasis, which is like increased signal amplitude after equalization. Whereas what we do on the transmitter is de-emphasis. Both are equalizing, but you are having a decreased signal amplitude. To make it more clear, consider that, let's say the channel response is this, okay, where I am having a 10 dB, minus 10 dB amplitude, minus 10 dB response. This is H of channel. Okay, if I want to compensate this 10 dB channel, I can do in two ways. I can have a response like this, let's say H equalizer 1, right? So where it also like it has a 0 dB here and minus 10 dB here, and the resultant will be, sorry, whatever. Okay, so the resultant signal swing will be this, right? If everything is linear, consider everything is linear in this case. Okay. Whereas I can also do this where I am having 0 to 10 dB positive, and then my final response will be this. Okay, H equalizer 2. So H equalizer 1 is actually doing de-emphasis, and H equalizer 2 is doing pre-emphasis. In both cases, you equalize the channel, but you have a smaller signal amplitude in the de-emphasis case. Okay. So we do equalization on the receiver side, and mostly it is a pre-emphasis kind of equalization. The drawbacks will become clear later. What's the drawback of doing a pre-emphasis also? Okay. So let's begin with the equalization on the receiver side. So what kind of equalization have we learned? We have learned only like a FIR equalization on the transmitter side. Whichever way be implemented, that is fine, but this is like delaying the signal and summing it up. Voltage mode equalization. So if you want to implement that thing at the receiver side, what would you do? Before going into any different kind of equalization, so this is termination, and I want to implement an equalizer. So what generally, what comes to your mind as such? Which kind of block? High pass filter. But high pass filter, so this is one difference. Why band pass? No, band pass will come, band pass, so it's like actually high pass till F Nyquist by 2. Right? There's a band pass only after that you consider, so let's not go that far. Just in terms of block diagram, you have implemented the FIR filter on the transmitter side by delaying the signal and summing it up with a different gain without any going into circuit detail. So that one was, you are having like flip-flops, and then they have different gain. This is equalized response. This is what we started on the transmitter side, right? Now, if I say that this is a received signal amplitude, what is the difference you see between this and when you implement it on the transmitter side. No, but that is, we know the bit pattern, but when we implemented this, we didn't use the bit pattern knowledge into account. In case of transmitter side, this VTX, if I say that was D of N, right? Automatically it got delayed by 1 bit period. So let's say we still know the clock. Let me assume that. I know clock. I know what data rate it is coming. Huh? If you know the clock, if you sample it at a clock, that's the part of a clock recovery. Clock recovery will try to put the clock in the center of the data. So if I want to, like whatever you are saying, so in case of the transmitter side, the signal was like this, right? And you always sample at the center of the signal. A fixed signal, let's say this is 0.5 and minus 0.5. In case of the receiver, what you have is, it is not that clean. It is basically more of a junk. It can be like all this is there. It can be anywhere, right? But I still am able to sample here somehow. But the amplitude variation can be a lot. That's the only difference. Hey, I need to just open the eye and sample the bit. Now what is the difference do you see? What are the challenges which you will face, which you didn't face when you implemented on the transmitter side? So do you see from the picture that on the transmitter side I draw only 2 voltage levels, plus and minus, fixed signal swing. The flip-flops which were used for the transmitter side, they were like a digital flip-flops. You just part a single sample. Whereas in case of receiver, you are having a different voltage at different times. It can be higher or lower. And ideally what we want to pass the same voltage on the next clock edge. So the flip-flop which was operating on a fixed signal swing, now the flip-flop has to operate on more or less an analog signal. So that is the difference which will come now. So on transmitter side, you have digital flip-flops to work with. On receiver side, for the same thing, you need an analog. Ideally, you need an analog flip-flop which can sample the voltage, transmit without disturbing the voltage to the next flip-flop. So have you seen any kind of like an analog flip-flop? What can be the simplest circuit which can sample an analog voltage and pass it to the next same block at the next clock edge? Huh? What thing? Track and hold, right? But you can now understand, for this simplest one, we are talking about a track and hold. There we had a good digital flip-flop, you can use a D flip-flop or any other thing, right? Where means that whatever is happening at the output will not change what is happening at the input. That's the flip-flop. At the edge it samples and rest of all the time the bit remains the same. Now, the simplest flip-flop which you have come is simple switch, track and hold. You sample at the clock, we hold the voltage, pass to the next. Pardon? That's about it. See, if you do not put any capacitor, what will you use to hold the voltage? First thing is, the capacitor will come automatically because you are having a real circuit. Another thing is, whether you want the capacitance to vary from one flip-flop to the other flip-flop, or you want the capacitance to be fixed from one flip-flop to other flip-flop, or you want to design it such that you still hold the maximum of the voltage. So you need some kind of, whether you need it, it will come automatically, but you need to have some uniformity between the capture from one flip-flop to the other flip-flop. And you are right that if you are using a capacitor, the voltage will basically drop, means for this capacitor and for this capacitor, right? Let's say it's very small, maybe even 2 or 3 femtofarad. But you charge this voltage, then you again charge through a switch, and this switch is not an ideal switch, it's a resistive switch. So you will have losses, you will drop, means you may start with, let's say, a 0.1 volt here, until the time you go to the 5th tap, you will have, let's say, 0.9 volt. Sorry, 0.09. It's not an amplifier. 0.09 volt. So you are not maintaining the signal. Okay. So this is only one first difficulty. The other thing is you are clocking. So if you use any switch to clock, you have a clock feed through coming in, which you will be injecting the charge in it, and the problem here is the signal which you are entertaining is actually a small swing signal. So if you disturb it, you do not know what's happening there. So it cannot be used like for more taps. Maybe you can try with 1 or 2 if possible, but that needs to be very carefully designed. And at high frequency, the thing is, let me just say, at high frequency, let's say you are talking about 40 Gbps data rate, for example, right? Time period is 25 picosecond. You can go to the best of the technology and then say in 25 picosecond my switch should sample the exact voltage, which means 25 picosecond should be equal to more than 3 time constant of this RC without any problem. So those things will then become difficult. It's not impossible, but then it may have another added ISI. You may try to cancel that ISI in some other manner. But if you are working at a lower frequency, 1 or 2 tap cancellation might be possible with this. And the other thing you see, right, that here, this is a sample and hold circuit. So clock to Q delay very much depends what is the voltage at the input, because resistance depend on what is the voltage. Resistance of the switch depends on what is the, like its drain and source voltages. So the clock to Q delay will vary. So clock to Q delay is in question. Then you have clock feed through. Sorry. Right? The leakage of a signal, leakage of whole voltage. So all these are the drawbacks to this circuit. But if there is no other way to do, you may try to get at least 1 to 2 tap cancellation with this. So one thing I think which should become little bit clear from this equalization, that on the receiver side you are working with analog voltages. You are not yet working with the full swing digital signals. Okay. So the easier thing is if we can get something in an analog fashion. Okay, so that means till now you have seen we have mostly dealt with the time domain waveforms. We have digital signals, we try to explain in that manner. Less in a frequency time, but they are like equivalent. Not equal, they are the same, whether you consider time domain or frequency domain. But here when the signal becomes analog, it's difficult to talk in terms of digital signals. So we will start dealing with the signal as an analog signal and start dealing with the equalization in frequency domain, where we are considering how the equalizer frequency response is used to compensate the channel loss. So one other thing which you can say that, okay, if I am having these flip-flops, I can use the buffers in between, right, to drive the next one. Now, if you use a buffer in between, you added a delay from clock to Q. What power consumption the buffer is going to have? Then that will come in question. Okay, so I think from next we will see more of an analog kind of equalization on the receiver side. Let me stop here.